Welcome to this lecture. This is the final lecture of week 7. In this week, we have discussed about the proof of equivalent statements for weak convergence. We have also seen the extension of weak convergence in higher dimensional setting, and we have again discussed some further equivalent conditions in the higher dimensional setting. And finally, we have looked at a very special example of the weak convergence, which is the central limit theorem, and this appears as some kind of a rate of convergence results for the law of large numbers. So, in this lecture we are going to discuss certain problems and exercises based on the content of this week. So, without further delay, let us continue the discussion using the slides. Alright, so let us discuss certain exercises and problems based on the content of this week. So, we start by recalling that in the first lecture, we had looked at the proofs of equivalent statements for weak convergence. In particular, we had concentrated on certain classes of functions being semi-continuous, in particular either the lower semi-continuous or upper semi-continuous. There were several exercises left out based on the semi-continuity properties of functions. So, we start by looking at one of those such exercises. The other exercises will go by using standard arguments. So, we do not discuss them. So, again just to illustrate the basic ideas, we discuss the solution to this exercise. So, here what is being asked is that given any open set G in the real line, look at the indicator function of G. So, we are supposed to check that this indicator function is lower semi continuous. So, let us see. So, we want to show that for all points, call them x naught, this inequality is true. So, here we are supposed to compute the liminf as x goes to x naught of this function, and that quantity should be greater or equals to the function's value at x naught. So, let us see, we consider two special cases. So, in the first case, what we do is that we look at the points x naught outside the open set G. So, here what is happening is that the indicator now is 0. So, because the point x naught is not in the open set G, but then the inequality will immediately follow, because look at the quantity involving liminf. So, here the function's evaluation that we are considering, these values are always 0 or 1s, and therefore, since we are considering the liminf of zeros and 1s, this will always be non-negative. Alright. So, therefore, this inequality immediately follows just by definition as long as the point is outside G. So, let us now consider the other case when the point is inside the open set. Now, here what we can see is that by the definition of an open set, we will immediately have a neighborhood of the point x naught. So, a neighborhood in the form given by some epsilon positive, that x naught minus epsilon to x naught plus epsilon, that open interval is completely contained in G. And therefore, if you look at this point coming from the interval now, essentially what is happening is that whenever you are considering the liminf, so for the approximation to work, for the approximation of x going to x naught to work, what we will require is that you have to have the x within a neighborhood of x naught, and that as per our description of the open sets, that will be completely contained inside this G, and therefore, here we can immediately compute that the liminf actually turns out to be 1 and matches with the function value, and therefore, we end up with the verification of the relevant inequality in both cases. In fact, in a similar way, we can also verify the case that if I take a closed set F, then the corresponding indicator function is upper semi continuous. So, in fact, the exercise 4 had two parts, the first part involving open sets and the second part involving closed sets, but the idea is essentially the same. You can also try to prove the second part involving closed sets in another way, that if you look at indicator of f, f is a closed set. So, therefore, f complement is an open set, and you can write indicator of f as 1 minus indicator f complemented. But since f complemented is open and we have already verified the lower semi continuity property of indicators of open sets, indicator of f complement must be lower semi continuous, but minus of any lower semi continuous function is upper semi continuous, and from that you can try to justify the upper semi continuity of indicator of capital F when f is closed. All right. So, let us move on and look at some interesting facts in connection with weak convergence and convergence in probability. Recall that convergence in probability always implies weak convergence. So, that we have already seen from our earlier discussion. But now, what we are going to check is for an example that will show that even if you consider random variables coming from the same probability space, and if you assume that these converge in the weak convergence sense, they may not converge in the convergence in probability sense. So, what it shows is that the convergence in probability is strictly stronger than weak convergence in the notion of convergences for random variables. So, let us see this example. So, what we now consider are certain independent random variables, call them x, x1, x2 and so on, with these very specific distributions. So, suppose x follows normal distribution with mean 0 and variance 2, and xn's follow normal distribution with mean 1 over n and variance 2 plus 1 by n square. Now, here you note that the corresponding means converge and the corresponding variances also converge. And therefore, if we go back to our earlier discussion in example 1, where we considered the weak convergence of Gaussian random variables, we will immediately conclude that our choices of x n must converge to x in the sense of weak convergence. In fact, this was also discussed earlier in remark 11 of the previous week. Now, here what we now consider is x n minus x. We have already assumed that x and x n's, all these random variables are independent, and since x follows normal with mean 0, variance 2 and x n's follow the normal distribution with mean 1 by n and variance 2 plus 1 by n squared, what we will immediately have that x n minus x follows the normal distribution with mean, the difference of the means, and variance, the addition of the variances. So, this is a property of the normal distribution. Here using the independence we are obtaining this result, that 1 by n is arising from this difference and the variance calculation is arising from the fact that the variances adds up by the independence. So, that is what we are using, and we have obtained the explicit distribution of x n minus x for all n. Now, again by our criteria we will simply have to look at the convergence of the means and the variances, and therefore, we will immediately conclude that as n goes to infinity, x n minus x converge to a random variable, let us say z, which is following normal distribution with variance 4. We now look at the case involving the convergence in probability. If possible, suppose x n's converge to x in the sense of convergence in probability. Then what is going to happen is that as a property of convergence in probability, we will immediately claim that x n minus x must converge in probability to the degenerate random variable 0, and in particular since convergence in probability implies the weak convergence, we will also have that x n minus x converges in the sense of weak convergence to the degenerate random variable 0. However, this last fact that we ended up having contradicts our earlier deduction that x n minus x converges to a non-degenerate random variable. So, this is a contradiction, and this contradiction arises because we had originally assumed that x n converges to x in probability. So, in this case the assumption must be false, and therefore, x n's cannot converge in probability to x. So, here what we see is that x n's converge to x in the sense of weak convergence, but not in the sense of convergence in probability. So, therefore, convergence in probability is strictly stronger than weak convergence. All right. So, now we go back and check certain nice applications of the central limit theorem. So, recall that we have discussed this Lindeberg-Levy central limit theorem or the classical central limit theorem in the setting of sequences of IID random variables. So, we now discuss an important practical application of this result. So, suppose you consider this situation that you consider a factory which produces some electric bulbs, and suppose the method the factory uses will produce bulbs whose lifetime now follows the exponential distribution with mean of let us say 10 months. Then suppose I am given a box of electric bulbs to test. So, here suppose it is given that the box contains 100 bulbs, and what we are interested in is that out of those 100 bulbs, suppose we want to check whether more than 20 of them will have a lifetime more than 10 log 2 months. So, this number 10 log 2 is just chosen for our computational simplicity, but you can also apply it to other numbers. So, let us just go with this 10 log 2 baseline for the corresponding lifetime, and we want to check whether out of these 100 bulbs at least 10 of them is going to have this much lifetime. So, in this case we model it in terms of random variables like this. So, suppose x denotes the lifetime of any randomly chosen such electric bulb. Then it is given that this number capital X, which is a random variable, is going to follow the exponential distribution with mean 10. So, we are going by the unit of months. Now, explicitly this distribution is given by this PDF, that if small x is positive, you have this expression for the PDF, otherwise this is 0. But now, let us look at the probability that a randomly chosen bulb is going to have the lifetime greater than 10 log 2 months. So, that probability is exactly given by this, and we can compute it in terms of the integration of the probability density function. Now, here what we want is that we want a integration of this probability density function over this range. So, if you explicitly put the expression of the probability density function and simplify, after the simplification you end up with half. So, this is for this computational simplicity we had chosen 10 log 2, but we can always go with some other numbers as long as we can do the explicit computation in terms of the probability density function. So, let us go with this number half. So, what we have just understood is that if we randomly choose a electric bulb, then immediately the probability that its lifetime will be at least 10 log 2, that is in the form that it is half. All right. So, now we now model it like this, that out of the 100 bulbs that we are given, suppose their lifetimes to be denoted by these things. So, these are random variables as long as we do not test them. So, now what we want to say is, before the experiment is performed, what kind of probabilities can we say about out of these 100 bulbs, more than 20 of them will have that much lifetime. So, now we can model these numbers or the random variables as independent with common distribution given by exponential with this 10 as the parameter. Now, here what we are interested in is whether the corresponding lifetime of the jth bulb is greater than 10 log 2 or not. So, that we can simply model by writing in terms of this random variable of the indicator type, that if the jth lifetime is greater than the 10 log 2 number, we will set it to be 1, otherwise set it to be 0. Now, it is immediately clear that these yj's are just 0 and 1 valued random variables for all these 1 up to 100, and since the jth random variable y is dependent only through xj, we will immediately have that the yj's are also independent amongst themselves. So, therefore, we are actually having these IID random variables with common distribution given by Bernoulli with parameter half. Recall that yj's are 0 1 valued random variable and yj is 1 exactly when xj is greater than 10 log 2, the probability of which is half, and therefore, we immediately have that all these yj's are independent and identically distributed with this common distribution as Bernoulli half. All right. So, let us now do the computation. So, what we are now interested is that out of all those 100 bulbs, more than 20 of them should have lifetime greater than that number, and that is exactly what we want in this probability. All right. Now, let us model it in terms of the central limit theorem. So, first of all, recall that since YNs are Bernoulli random variables with probability of success half, if we add up these random variables, so since they are independent, their sum will now follow the binomial distribution with these parameters 100 comma half. But if we want to compute our probability of interest, this will be a very complicated calculations in terms of the probability mass function of this binomial distribution. If we do not want to directly compute this number, what we can do is that we can do this approximation through the central limit theorem, and this is where the approximation result uses the Lindeberg-Levy central limit theorem. So, let us see the idea. So, we are going with the fact that yi's are IID and the common distribution is Bernoulli with probability of success half, and therefore, the expectation is half and variance is 1/4. This you can immediately check. Therefore, if we center and scale the sample mean like this, then it will have approximately normal 0 1 distribution for large enough n, and this approximation is in the sense of weak convergence of random variables. Now, this is what is the application of the Lindeberg-Levy central limit theorem, and what we simply do is that we put n equal to 100 and obtain that centered and scaled versions multiplied by the square root n that number. So, now what we do is that this random variable now we are going to think of as our random variable z, which follows normal 0 1 distribution. So, this is the approximation that we get from the central limit theorem. Now, our probability of interest, we will simply write it in terms of this random variable. So, let us do this algebraic manipulation, simple algebraic manipulation, and our probability of interest can be rewritten by some appropriate simplification like this. All right. But then we also observe this is that this random variable takes the value greater than -6, which can also be thought of in terms of 1 minus this probability. But this is what? This is the probability of this random variable taking value less equal to -6, but therefore, this probability that we are interested in is actually the distribution function of this random variable evaluated at -6. But now, through the convergence in distribution, we must have the pointwise convergence, and that is what we are using, that we can replace this by the approximated value from the distribution function of the standard normal random variable. So, this is the approximation that we are getting through the central limit theorem that we have discussed earlier, and this therefore, is giving us an approximation of the probability of interest through the distribution function of standard normal random variables. So, we have seen some nice application of the central limit theorem in this setting, and we have also discussed some other applications of weak convergence in this lecture. So, we are going to stop here. So, we continue looking at further properties of weak convergence in the next week. We stop here. Thank you.